Alright, so while the last video might have been a little difficult to imagine, and might have been new for most of you, this next one is not. The Chateliers Principle, or Le Chatelier, sorry, that's how the French say it, is something that we covered in general chemistry and something you've seen before. And it's basically that if a stress is applied to a system at equilibrium, the position of equilibrium will shift to undo that stress. And one of the common examples I use is on a treadmill. If you're on a treadmill, you're at equilibrium. You are running forward at the same rate that the treadmill is going backwards. And if I, being the mean, evil person that I am, come up and turn the treadmill up, I apply a stress to your system, you are going to have to run faster to undo that stress. In chemistry, it's the same thing. Anything that affects either the forward or the reverse reaction more so than the opposite, so anything that affects the forward reaction more than the reverse reaction, affects the rate of the forward reaction, is going to be a stress, and it's going to cause equilibrium to shift. So when I teach this in general chemistry, I teach it as you have a piece of wood on cinder blocks with a red ball in the center that we're going to call equilibrium. And when we're at equilibrium, the ball sits perfectly on the center piece of this wood, and it's not going to go anywhere because we're on nice flat level ground. So there are a couple things you can change that will cause this ball, will cause equilibrium to shift, to undo that stress. So first off, the easiest one is changing the concentration. So let's just say I'm going to change the concentration of nitrogen gas. So if I remove nitrogen gas, that means I'm going to take away one of the cinder blocks on this side. So our equilibrium, our little piece of wood here, is going to drop down like that. Now which way is the ball going to roll? Well, with gravity, the ball will come down this way. So equilibrium will shift towards the production of more reactants. So we're now going to have a larger arrow in this direction and a smaller arrow in the forward. So which way would equilibrium shift? It will shift towards the reactants. Which makes sense because if I remove some of this nitrogen, now there's more space for ammonia to decompose into nitrogen and hydrogen gas. So our concentration of nitrogen will increase, our concentration of hydrogen will increase, and our concentration of ammonium will decrease. In general chemistry, I teach them that if you wanted to hold this, get this piece of wood to go flat again, you would have to raise it on this side and lower it on this side. So everything on this side will go down, everything on this side goes up. And once you did that, equilibrium would be reestablished. So we would have to lift up on the reactant side, push down on the product side. So the concentration of our reactants will increase, and the concentration of our products will decrease. Alright, what if you add hydrogen? Sorry, I've caught a summer flu, so if my voice is all over the place, my apologies. Or a winter flu. So if I add hydrogen, that means I'm going to add a cinder block to this side. So what's going to happen? Well, our little blank of wood is going to dip down, and our little ball is going to fall this way. So this means that our equilibrium will shift towards the production of more products, because now that we have more reactants that can react, they will produce more products. And how would I get the ball to lie flat again? Well, I would have to push up on this side and push down on that side. So that means that concentration of products will increase, and our concentration of reactants will decrease as we use up those reactants to produce products. Another thing that you can change that will alter equilibrium, that will add a stress to the system, would be to change the temperature. And when you have a problem like this where they give you the delta H, it's often easiest to rewrite this so that temperature is part of the reactant, or is part of the reaction. So since we have a negative delta H, that means that this is an exothermic reaction. This means that heat, or this change in temperature, change in heat, this enthalpy, is a product of this reaction. So I'm going to rewrite this, get rid of the delta H, and simply say plus 92.2 kilojoules. And when when you rewrite it like this, it's actually very easy to imagine, okay, so I have these reactants coming together to form this product and temperature. If I change the temperature, you're going to treat it just like we did with changing the concentration. So if I cool this down, if I decrease the temperature, that's like taking a cinder block from this side, because since temperature is on this side of the reaction, I'm going to take it away. What's that going to do to our plank of wood and cinder block? It's going to tilt down like this, which means to undo this stress, to undo this decrease in temperature, the system is going to go through the forward reaction more to produce more heat. So equilibrium will shift towards the production of products. On the flip side, if I heat this reaction up, it's going to add a cinder block to this side, which will cause our plank of wood to dip this way, so we will know that that's going to shift the reaction towards the reactant side. So we've made this reaction hotter. It's going to try to cool itself down by producing more reactants. Another question the AP exam loves to ask is, what would happen to equilibrium? Which direction is equilibrium going to shift if I add a catalyst? Now this one, our little ball and cinder block analogy is not going to work out so well, so I'm going to get rid of it. And instead I'm going to bring back an old friend, an energy diagram. Okay, if you have a reaction, so this blue line represents the reaction and its activation energy. The addition of a catalyst simply lowers that activation energy, but it does so in both the forward and the reverse reaction. And therefore, would adding a catalyst have any real effect on the rate of this reaction in either way? Will it favor one over the other? No, because the forward reaction and the reverse reaction are both being affected equally by the addition of a catalyst. So here's a lot of free points on the AP exam. If they ever ask which direction will equilibrium shift with the addition of a catalyst, it is always going to be there will be no effect on the position of equilibrium. Equilibrium will be unaffected by the addition of a catalyst. You can also adjust the volume at which this reaction is occurring, and changing the volume is going to add another stress to our system. And again, it's not going to be useful to see the cinder blocks and wood analogy. For this one, you just kind of have to imagine it. Okay. If you change the volume, essentially you're changing the pressure. And especially when you're talking about gases, changing the volume is going to have the greatest effect on gases. So what happens is, if I increase the volume, sorry, for copy and pasting sake, I'm just going to do decrease first. So if I decrease the volume, what does that do to the pressure? If I decrease the volume, I'm going to push down on this gas. That means that it's going to increase the pressure. What can this system do to undo that stress, to relieve some of that pressure? It can go to the side with the least number of moles of gas. So on this side of this reaction we have 1 plus 3, we have 4 moles of gas. On this side we have 2. So if I decrease the volume, thereby I increase the pressure, to undo that stress, this system would shift towards the production of products. Notice that I said this system, because this is 4 moles of gas to 2 moles of gas. You need to look at the number of moles of gas. That's why you can't use this analogy for that. You have to kind of look at it. And the opposite, if I increase the volume, that means I'm going to decrease the pressure. Now that system has more room to expand. There's less pressure. What can it do to use up or to replace that pressure? It will go to the side with more moles of gas. So from 2 moles to 4 moles, so it will produce more reactant. Again, that is specific to this system. You have to look at the number of moles. 4 moles to 2 moles. It's not always going to be the same. What would happen if I had the same number of moles on each side? Let's say if I was special and I didn't actually have this balanced. Let's say it was 2 moles to 2 moles, like this unbalanced reaction. That's why balancing is important. If it were 2 moles to 2 moles, is there anything, can I shift one way or can I shift another that's going to undo that stress, that change in volume, and thereby that change in pressure? No. So if you have the same number of moles of gas on both sides, changing the volume and changing the pressure will not have an effect on equilibrium. This is why balancing is extremely important. The very final question you'll often get with Chateliers Principle deals with K. And you need to remember that K is products over reactants. So if you cause equilibrium to shift so that it favors products, that means that your products' concentration are going to increase and your reactants will stay relatively the same. So what will happen to K? Well, K will cause an improper fraction, will be a larger whole number, so K would increase. On the flip side, if you cause equilibrium to shift towards causing your reactants concentration to increase, now you'll have a fraction and K will decrease. So anytime you're asked to predict what will happen to K, you need to look at which way equilibrium shifted and keep in mind that it's products over reactants. What is increasing and what is decreasing? What is changing here? Alright? So for these two, change in K and change in volume or change in pressure, because they're related, especially when you're talking about gases, you kind of have to visualize. You got to look at your equation and see what you've got. But for change in temperature and change in concentration, you can use that ball and cinder block analogy. There are a lot of different ways to go about thinking about it. If you're more the conceptual chemistry way, you can think change in concentration, what is taking up more room, what reactions, what molecules are going to collide more often, change in temperature, heat them up, speed them up kind of thing. I always rely on the cinder block method. Again, whatever works best for you. Chateliers Principle.